Hello. This will be a demonstration of proposition 11 from book 2, which states to cut a given straight line such that the rectangle contained by the whole in one of the segments equals the square on the remaining segment. We're finally at a QEF after 10 propositions in book 2. All we are given is the straight line AB. That's all we're given. And on AB, the goal of the proposition is to cut AB such that the rectangle contained by the whole in one of the segments equals the square on the remaining segment. So let's get to it. First, we should begin by describing the square ABDC on AB. And we can do this by proposition 146. Make that look nice. ABDC. Next, we shall bisect AC at point E. So now AE equals EC. We can do this by proposition 110. Next, we can join the straight line BE, that's postulate 1. Next thing we shall do is that we shall extend the straight line CA to point F, and we shall make EF equal to BE. So that would put us at about here, let's say. So we know that EF is equal to BC. And then on AF, we're going to describe the square AFGH, again by a proposition, that's not that good. Again, by proposition 146, we can describe squares on finite straight lines. AF is evidently finite. It'd be quite strange if it was infinite. So that's good enough. So there's our square AFGH on AF, proposition 146. And finally, we shall extend the straight line GH through to point K. And K is all the way down here on CD. And that's our whole construction. Now, by proposition 26, which states that if a straight line be bisected and a straight line be added to it in a straight line, the rectangle contained by the whole and the added contained by the whole plus the added straight line and the added straight line plus the square on the half will equal the square on the half plus the added straight line. In this case, we shall say that the rectangle contained by CF and FA, the whole here in this case, or the bisected straight line, will be AE or AC at point E, and the added straight line will be AF. We can say that the rectangle contained by CF and FA plus the square on the half, in this case AE, so plus AE squared, will equal the square on EF, which is the half plus the added straight line. The half being AE and the added straight line being AF. The rectangle CA times FA plus AE squared will equal EF squared. Again, we know that by proposition 26. We also know that EF is equal to BE. We made it that way in the first step. And so by a property of magnitudes, we can swap out EF squared for BE squared and say that the rectangle contained by CF and FA plus the square on EA will equal the square on BE. We also know that the square on BE, subtending a right angle, right there. We know it's a right angle because it's a square. It's an angle in a square. We know that the square on BE will equal the square on AE plus the square on AB. And so we can say that the rectangle CF times FA plus AE squared will equal BA squared plus AE squared. Subtracting equals from equals by common notion 3, we shall say that the rectangle CF times FA will equal the rectangle AB. There it is. I was looking at the wrong step. So again, we know that BE squared is equal to AE squared plus AB squared. That's proposition 147. And so things equal to the same thing are equal to one another, so we can say that the rectangle CF times FA plus AE squared equals AE squared plus AB squared. Subtracting equals from equals, namely AE squared is on both sides, so we can subtract it. And we can say that the rectangle CF times FA equals the square on AB. We also know that AF is equal to FG. How we know this? Well, they're two sides of a square, and so they must be equal by the definition of a square. It's definition 122. And so we can say that the rectangle CF times FA will also equal the rectangle CF times FG. That's a property of magnitudes. And the rectangle CF times FG is the rectangle FK. And so we can say that the rectangle CF times FA equals the rectangle FK. Oh, excuse me. And so we can say that the square AD, which is AB squared, is equal to the rectangle FK. So this rectangle right here. And then if we subtract the rectangle AK from both of them, we shall get equals as well because of common notion 3. And so we can say, well, if we subtract AK from FK, we simply get FH. And if we subtract AK from AD, we simply get HD. And so we can say that the square FD is equal to the rectangle HD. Right? Finally, we know that AB is equal to BD. We know this by, that's a little confusing. We know that AB is equal to BD because of, well, they're two sides of a square. That's definition 122 again. And so we can say that the rectangle HD being contained by HB and BD is equal to the rectangle contained by HB and AB. We also know that AF is equal to AH, again, because they're two sides of a square, and so they're equal. And so we can say that the square FH is equal to the square on AH. And so by common notion 1, we can say that the rectangle AH times HB, which is equal to the rectangle HD, is equal to the square on AH, which is FH. And H being on AB, we are actually done with the proposition because we have cut the straight line AB at a point, namely H, such that the rectangle contained by the hole in one of the segments, in this case the rectangle contained by AB and BH, is equal to the square on the remaining segment, namely AH. Right, so we've cut AB at point H such that the rectangle contained by AB and BH equals the square on AH. And this being what we set out to prove, we are done with the proposition QEF. I don't have anything to say about this proposition, but I'm quite happy to do a construction. So I will end the video here and I will move on to proposition 212.